Okay, so now that we have covered Newton-Euler formulation, and we also did one of the example of one-link manipulator using recursive Newton-Euler approach. So we now know general Newton-Euler approach to derive equation of motion, as well as recursive Newton-Euler approach, where we have a formulation with which you can do calculation of forces and torques recursively, starting from all the joints, right from the end joint to the first joint. That is the backward iteration we did. And we also did forward iteration when we calculated all the velocities and acceleration of each length using forward iteration of Newton-Euler approach. So that was the approach of recursive Newton-Euler. So today, continuing further, we'll do two-link manipulator using recursive Newton-Euler approach. So now we'll do 2R manipulator using Newton-Euler approach. 2R is two revolute joint, that is planar manipulator, that we'll be doing now. Okay, so let us begin. So yes, this is the planar manipulator. We have been dealing it since a long time, even with forward kinematics, inverse kinematics. This is the one which is very, very important, you know already. But in dynamics, if it is a planar, it becomes very, very simpler. So as because recursive Newton-Euler approach or Newton-Euler approach in general involves plenty of equations to deal with, it is normally comfortably we can do using programming, but in order to do analytically on pen and paper, it is very, very difficult to move ahead to. So in order to demonstrate that, the basic principle, I am proceeding with 2R planar manipulator only, so that we can handle the equations very well. So yes, this is your two-link manipulator. Moment of inertia of the first link is given by I1, and you have mass m1. LC1 is the center of mass distance from one of the end, that is here, attached here you see, and total length is L1. Similarly, LC2 you have, that is the distance of center of mass location with respect to this end of second link, and total length is L2. VC2 is the velocity of center of mass of second link. Similarly, VC1 is also there. So yes, you have tau 1 and tau 2 which is required to be found out. Forces, interaction forces are F1, 2. You see it is here, that is the interaction forces between the links. Okay, so this is how it is all defined, and you have X and Y axes are fixed like this. So you have Z axis which is rotating out of this plane, and those are placed here and here. Okay, so let us continue. So yes, the first Newton-Euler equation for link 1 is for the force and force of interaction. It is 0, 1 and 1, 2. So it is for link 1, you see, for this link. Okay, so F01 acts at this end. F12, you see it is acting at over here. And M1G is the force due to the gravity that you see, M1G, and it is directed along the Z direction. And you have M1 VC1 dot. So why is it VC1 dot? If it is the center of mass velocity given by VC1, so VC1 dot is the acceleration of center of mass. So that is here. So this is inertial force, this is gravitational force. These are the two forces externally acting on link 1 isolated. Okay, so this is the force balance equation. Similarly, we can write moment balance equation. So this is the moment that acts here, and similarly you have moment that acts here. Okay, N1 and N01 and N12, and these are the moments due to the reaction forces, the joint reaction forces. So this is one force, and you have the distance which is given by C1, that is this one, and that is the vector actually, and similarly 0 C1 is this one. So you have this force. So these are just cross products which is giving you clockwise and counterclockwise moments, so that those goes here, and this is that is because of angular acceleration. So finally it is moment balance equation, so it gives you 0, as because it is a vector equation, so this should be 0 vector, that is 0 0 0, it should be like this. Okay, so this is for the link 1. Similarly, so note that for inertia tensor, it is a scalar in this case, because if it is planar, it is only in one direction you are interested in, and more so we have simplified this link. Okay, it is slender bar and you have center of mass situated at the center. Okay, centroid of each link is assumed to be at its center. Okay, similarly, Newton-Euler equation for link 2 is F12, that is the force which acts over here, and there is no external force that is acting from here, so you don't see the other force. You have though the gravitational force, that is m2g, and this is the inertia force. It is mass into acceleration. Okay, so this is the velocity of center of mass. So that is what you know already. So this is the force balance equation, and this one is the moment balance equation. And again you have moment acting only at this end. Okay, so that is getting into this second link. This is your second link, and this is the moment generated because of the force balance. So that is what you are getting. So this is moment because of force, so that comes here, and you have inertia moment due to the inertia. So because this has a angular acceleration of omega 2 dots, so if it is omega 2 dot, so inertia of the second link is I2, so that comes here. Okay, so these are the two equations, Newton-Euler equation, that is for link 1 as well as link 2. Okay, for the planar manipulator, moment can be given as 0 0 tau is nothing but the torque at the joint. Okay, it is exactly lying at the along the z axis, 0 0 tau, so this is your n vector. Okay, so that can be, and similarly for both the links, for 1 and 2, it is tau 1 and tau 2. Those are the joint torques which you want to find out. Okay, so that is what it can be written like this. Okay, so now eliminating F12. What you can see here, we want to extract F12, which is here, F12. Okay, F12. So we have to substitute F12 from one of the equation to the other one. So just look carefully. It was there somewhere in this. Okay, so F12 from here, I am substituting it here so that gets eliminated. So as soon as you substitute here, whole of this will come here in the bracket, and then you expand this. So that is what is obtained. Okay, so you got this, and moment you can replace it with the torque like this. Torque here is exactly the moment, and that is along. So moment can be written as torque 2 along z. If it is z, it can be written like this. So both are equal magnitude wise, so I can write it in a vector form like this also. So both equivalents I have taken. So torque 2 vector is nothing but 0 0 tau 2. Okay, so this is the magnitude, and in terms of vector can be written like this again. So here goes the original thing. So both are same, and I have just substituted F12 from the moment equation of second link, so that comes, those terms comes here. So that is expanded form. I can write it like this. The last term was exactly this one. So again, for the link 1, I did exactly the same thing. Again, I should show you this. So you see it is here. So I can substitute. This time I want to eliminate F01. So I can substitute F01 directly. Okay, F01 and F12 from the second link equation. Everything goes to the second equation of link 1. Okay, so F01 and F12, F01 from here and F12 from the second link equation, both are substituted to the moment equation of link 1. Got it? So now what do I get? I simply can write it like this. Okay, So it looks quite expanded and difficult, but actually they are derived out of two fundamental equations, Newton equation, Euler equation, that is the force balance and the moment balance equation for the link 1 and link 2. So immediately you can write it like this. Got it? So now solving this and using some terms which are like this. So theta 1 and theta 2 are the joint variables. So you can write omega 1 simply as theta 1 dot. Similarly, omega 2 will be sum of angular velocity. If it is written in the zeroth frame, that is the ground frame. So angular velocity is theta 1 dot and theta 2 dot. Sum of those. Okay. That becomes the total angular velocity for the second link with respect to the ground frame. Okay, and C1 and C2 are the locations of center of mass with respect to the base frame, that is the zero frame, first frame. Let me just show you once again this figure. So it is this frame. Okay, it is about this frame, you see. Okay, so these are the two center of gravity location for any angle theta 1 and theta 2. So these are variable locations. Now I can calculate the velocities by taking differentials of this. You take derivative with respect to time. So from this you can obtain this, and from this you can obtain this. Got it? And similarly I can also obtain the acceleration by taking double derivative of this also. So yes, now that you have obtained Vc1 dot and Vc2 dot also, you can obtain by taking derivative of this. Substitute that here. You see it is quite lengthy. Even for just two links it becomes very lengthy equation, and you have to handle analytically with symbols for such a long equation. It becomes really difficult. Okay, even for a planar case like this. So now I'll substitute this all here. Okay, omega 1 and omega 2 will also go there. Okay, from here and from here. So that can be written like this. So omega 1 in case of vector you can write it as omega. If it is a vector you can write, because you know it is along z axis, so it becomes 0 omega, the value that you have obtained, omega 1 and omega 2. Inertia here you can write it in terms of inertia tensor over there. Okay, so that can be quickly written over there. And this equation, this is as simple as that. So g is simply 0 it is along negative y axis, so it is can be written as 0 minus g and 0. You see, if you just check your frame, so it is like negative of y axis. So that was your direction, and all those substituting here you can obtain the generalized closed form dynamic equation of motion like this. So now you have to organize those all elements in terms like this. So this becomes your generalized inertia matrix. So you have to write the scalar equation of tau 1 similarly for tau 2 and pack them together the way we did it in Lagrange-Euler's equation. Okay, so same way you can arrange them in this manner. So you get generalized inertia matrix, centripetal term, Coriolis term, and the gravity term. So you now know already the physical significance of each one of them we have discussed earlier. Okay, so explaining them further. So the terms of generalized inertia matrix are, so if you write inertia matrix as I11, I12, I21 and I22, so this term can be explained like this. So this is basically moment of inertia of combined both the lengths. If you put them together, so if you freeze them, so this is your theta 2, this is your theta 1. So at any instant, if it is frozen, you have to find out moment of inertia of this combined structure with respect to this. So that is what is this. With joint 2 immobilized at an angle theta 2, this is theta 1. If you for any particular angle, so this becomes your moment of inertia about this. So because you want to find out moment torque at this joint, so this term exactly tells you combined moment of inertia when the robot is like this. Got it? Next term is I12. Again, I11, I12. This basically I12 and 21 basically are interaction between the two links. Okay, so because of the combined action between the two links in motion, so this is the moment of inertia. So this one is the pure moment of inertia, and this also will be the pure moment of inertia, but this one and this one is due to the interaction between the two joints, and that is given by this moment of inertia. This is what was physical significance we have seen earlier also. And I22 is nothing but moment of inertia of link 2 about joint 2. This is the simplest one. Okay, so if this is your link 2, you can quickly find them. Okay, if this is your x, this is your y, you can quickly find out moment of inertia of link 2 about its own joint, this one. So it is nothing but, if this is L2 and you already know moment of inertia about this, okay, that is I2. So I2 and ML2 square, so that is I22. So now you know you have all the four terms in, and diagonal elements and the interaction terms. Okay, so centripetal terms are these. Similarly, Coriolis terms comes out to be the same, exactly same as we have obtained using Lagrange-Euler formulation also. So the terms are similar, and the gravity terms also we have seen earlier. Okay, so this is the effect of center of mass that is getting pulled due to the gravity, and this is the torque that you will see even when the system is not in motion. It is static at any particular location given by joint angles theta 1 and theta 2. So at any particular instant, this should be the torque that acts at joint 1 and joint 2 respectively. Okay, so that is the gravity term. So this is all we can obtain even using Newton-Euler formulation, you see. Okay, so there are some pros and cons of each of these algorithms. So in case of Lagrange-Euler formulation, you have seen it is multi-body robot. It is seen as a whole. You have calculated the total energy, kinetic energy and potential energy of the whole system. You have considered together. So whole body is considered even to calculate just the joint torque at one of the link. Okay, so that is how you have considered, and you have calculated. It is an energy based approach, you have also seen that. And constrained internal reaction forces between the links are automatically eliminated. You see, it is automatically eliminated. In fact, they do not perform any work, so that is not important as well. Okay, so it is not calculated on the way when we calculate the joint torques also. So yes, this is not important, but sometimes they are important. If you want, let us say you want to find out the joint interaction force, you want to design the shear load on one of your bearing or one of the shaft that goes here. So definitely you need to know the interaction force that is coming on to that. Okay, so in that case, Newton-Euler formulation will help you if you want to design that joint. Okay, otherwise getting rid of that makes things much simpler. So you can follow Lagrange-Euler formulation. Closed form symbolic equation of motion is directly obtained. You see, you have obtained the equation of motion directly, and that too in symbolic form very easily. Whereas in case of Newton-Euler also you could obtain, but it becomes very lengthy. You have seen the process for tooling just now, so it is not that trivial. Okay, best suited for study of dynamic properties and analysis of control scheme. When you want to analyze how your robot will behave, so now that you have symbolic equation in hand, you can quickly obtain the behavior. You can obtain the transfer function, taking whole of the robot as a single unit. You can make a model based control. You have whole equation in hand, and you can calculate torque for any given joint velocities and accelerations. So provided you have the symbolic equation in hand, these things becomes very simple. In case of Newton-Euler formulation, dynamic equations are written separately for each of the body. You see, each link you have made a simple force and moment balance equation, attempted all of them, approached from one end to the other end while calculating your velocities, and in the backward manner when you calculated the torques at each joint. So that is what you did. Okay, inverse dynamics is done in real time. Equations are evaluated in numeric and recursive way. Okay, numeric and recursive way. If you are doing in program, so you are doing all of them in a numeric way. You directly get the values. You don't get anything in symbols. So, and recursively, you do forward, you do backward, and you get the velocities and the torques, you see. So everything is calculated at every instant of time. Okay, and it is best for implementation of model based control scheme also. You don't need forward solution, that tau is equal to I theta double dot, C theta theta dot, and gamma theta for a complex system like robot. Okay, if it is multi-link, it is really complex, so you can handle things even numerically. That doesn't mean you are solving with some iterative techniques, definitely. So you here numerically, I mean the values you get directly in hand, you do for every moment, every instant of time, and you use them. Okay, so elimination of reaction forces and back substitution of expression, we still get a closed form dynamic equations as in Lagrange-Euler or Euler-Lagrange technique. So we got reached to the same place, you see. But this Newton-Euler approach, you see, it is the way it is formulated, it allows programming very easily. Okay, so that is the reason I personally have preferred this one. But yes, there are, I won't say Lagrange-Euler doesn't have any recursive or programming approach. Yes, it do have. There are books which is covering even Lagrange-Euler in that manner. Okay, so take derivative, you have a matrix which is defined. If it is pre-multiplied, you directly get the derivative of any transfer function, like a transformation matrix. Okay, so that is how even Lagrange-Euler is dealt quite a lot of times. But yes, depending on situation, you can use any one of them. But this is quite okay. If you have to do some control scheme, like model based control scheme, this is quite okay. Okay, so with that I would end dynamics. Okay, and the next module I will be covering directly your load data calibration, that is the payload and the supplementary load that needs to be calibrated before you put your robot to use, because you know nowadays the robots are huge robots. Sometimes for example KUKA Titan, it is a class robot of something around 1 ton capacity. It can carry near to 1 ton, and even Fanuc has it. So you see, it carries a huge payload. So as soon as the robot picks up the load, the dynamics changes. Okay, you need to know where is your new center of gravity location. So you have to calibrate your load. Okay, where it should be picked up. If your gripper, how long is your gripper? Okay, how that is going to affect your system. So whole of the dynamics, now you know dynamics, you know how it changes your system. If moment of inertia and mass center of location changes, so yes, it is going to drastically change your torques that is going to come onto your links, onto your joints. Okay, so payload and supplementary load correction is to be done. Some identification experiments are required. So all those we will be doing. You see, your link, as soon as you load with some supplementary load or with cables and some few things which are not actually meant to be there, but now after the design they are loaded. So those informations are missing to the controller. So we need to do some sort of experiments. So we do those experiments to identify the mass center location and actual value of mass even, and the moment of inertia of your robot, so that you exactly can calculate the complete dynamics of your system. So these things are very predominant in case of huge robots. Okay, so with that I'll end here, and this chapter in this module, that is dynamics. So see you in next module, that is load data calibration. That's all. Thanks a lot.